We'll get our next homework assignment on Wednesday. It'll be over population growth models. We will start playing with those by the end of class today, but when we get to the big example that we'll work through the whole problem, we'll of course keep that until Wednesday and do that the first hour, and then you'll have the second hour to do your homework. Our next exam is October 30th, and so well after fall break, so we're still good there. Next week, we don't have class on Monday, but we have the double one on Wednesday. Hey! All right, any other announcements or questions? Anything needs to be addressed? Okay. So we are finished now with our life tables. So hopefully we got those down. And we're moving into population growth models today. We'll do that this week and next week. And then we're going to go into social structure, I think, like mating systems and some other stuff like that. I do that on purpose because we got like two big models back to back, and then we'll take a break, and then we'll come back to modeling essentially. So I think that's what we have coming up. All right, so let's jump in. So population growth is what we're often interested in. So is a population increasing and decreasing, and what kind of predictions can we make? There are two basic models of population growth, and this is not the exponential and logistic, although I'm kind of counting on all of you who haven't heard those words before. This is referring to the overall category of models. And so one type of model is a finite model, and a finite model is very short term. It looks at a change in the population over a very specific, distinct, discrete period of time. And generally it's only useful for organisms that are basically annuals. They live and die in a single season. And because it is such a short period of time, it is highly influenced by annual fluctuation. So what you get this year won't match what happens next year, depending on droughts and floods and all of that kind of stuff. We are not going to work with this type of model very much, but we are going to learn how to calculate a finite growth rate. All right? And the finite growth rate basically looks at your growth rate over one time unit. And so I've kind of tried to get you to start thinking about this, but a lot of the times our time unit is a year, but sometimes, depending on the problem you're working with, it might be a day or a week or a month or something like that. So if we're doing an organism that's fairly long-lived, then your finite growth rate would be how much the population grew or decreased between this year and next year, and that's it. That's all it's good for, is a single year, a single time unit. Okay? Following so far? Told you it was going to be too much thinking for Monday morning. All right. The second type is called an instantaneous model. And I think this term often confuses people because you think in an instant. And that is part of it, but what you're really doing is you're taking a measure of what's happening in the population at lots of instances over time. So that's where the long-term part of this comes from. And so you do look at population change at an instant, you get little snapshots, but you average them long-term. This is useful for species that are a lot longer lived. This is really going to stress the long-lived on this slide. But we'll see that we can also use them for fairly short-lived. If we change our time scale, we can do that. It's not influenced by annual fluctuation like a finite model. And so these are the ones that we are going to be working with. So our homework will be using instantaneous models, except for when I ask you to calculate a finite growth rate. That would be a part of a finite model. So I was trying to think about how to get this into your head, because with a finite model, let's say we have a long-lived species again, so our time unit is years. And so a finite model, if we're calculating the growth rate, we're going to look at what the population size is this year, what the population size is next year, and then we're going to figure out what the growth rate was for that year. That's a finite model. For the instantaneous models, what we're going to do is we're going to look at the population size here, 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 lots of times over a span of time, and we're going to get a line that represents that particular population. And so what that's going to do is, if you think about, you've probably seen like scatter graphs before, maybe. So it looks kind of like this. And then you fit a line to it, and some years the population might be growing faster, and some years it might be growing slower. That's really what this model is trying to get at, is trying to average out all of that fluctuation. And I think the reason we get confused sometimes is because with finite, it is just, it's 1 year to the next. And what we're going to do for our models is we're going to get a population size usually at time 0, so whatever that population size is, whenever we start watching it, I'll make a mess. And then we're going to have a population size sometime in the future, and we want to know what the growth rate is along that line, all right? In other words, in your homework problems, you're going to have 2 points in time that you're working with. But those 2 points in time would be better if we had lots of points in time, but that's a lot harder. But it's still going to average out what happened over this time period. Right? So any fluctuations where your higher or lower growth rate that happened over this time period, it's flattened out when you look at this straight line. Does that make sense so far? Sort of? Okay, the other thing that happens is if we look at 2 points in time like this, is we do get a straight line. And working with a straight line is fairly easy. There's a whole straight line formula that we'll be reviewing a little bit later that allows us to do things like estimate the slope of the line and stuff like that. Okay, don't worry if it's been a while. We will review all of that. All right, any questions between a finite model and instantaneous model? Other than one of them's short term, one of them's long term. Just try and get you to think about them a little bit more. Because I find that when we do our problems, it's not hard to calculate the finite per capita growth rate, which is going to be capital R, which we'll get to a little bit more. I guess we're going to get to it on the next slide, actually. But for some reason, people kind of get a little stuck on that it's just 1 year apart. It's not your actual data, it's just 1 year, okay, or one time unit. Okay, now our brain can take a little bit, don't take a break, but it shouldn't be quite as intense. So like I did for the life tables, I'm going to kind of take some time and go through this and every single one of these little X's and Y's and all this stuff very carefully. So some of you may be familiar with these, some of you may not, but I've just found that when we take the extra time to do it, we tend to do a little bit better later on. And so we've already seen N. N is our population size. T, a lowercase t, is time. And then here's one difference we have from the life tables. In the life tables we had nx, and the x was changing all the time. And so now what we have is population size at time t, and the t is going to change. All right? And so just like we had with our life tables, we're usually going to start with N0, which is your initial population size. And then maybe we're interested in what the population is 100 years from now, and so that would be N100. Okay, so it's going to change with your time units. And I forgot we got it so quickly until I looked at my previous slide. But here is our finite or short-term per capita growth rate. Per capita means per individual. That's what per capita means. We hear it a lot, might not necessarily know what it means. And so as you look at this formula, you have your capital R, which is short for your finite per capita growth rate. And then you have it equals NT plus 1. All of this is a subscript again. And so that plus 1 refers to the time. Over NT. Okay? And so the way we'll calculate this most of the time is in your problem, you're going to say, it's going to say something like 100 parakeets populated this island. All right, that's your time 0 essentially, when it populated the island. And so that's your N0, your N0 is 100. All right? And so most of the time, that's what we'll use here, is we'll just put 0 because we always have that number. And so this becomes N0 plus 1, or N1. Right? But you can do it for any time period. And so a lot of times our question will be 100 parakeets colonized this island. 50 years from now, we have 250 parakeets. All right? And so what we could do is we could do N 250 here. And then this would become N 250 plus 1, or 251. And you're still looking at the growth rate over a single year. And you'll get the exact same answer. Okay? So it doesn't matter what year interval you use, you'll get the exact same answer. All right? But like I said, most of the time, the easiest thing to do, the easiest thing for me to check, I think we all do the same thing especially, it's just do you start with N0, because you're always given N0, your initial population size, and this just becomes N1 divided by N0. What's the growth rate over that first year? And then according to our exponential growth model, which is what we're working with right now, we're getting ready to, it's not going to change. All right. Then we have our instantaneous or long-term per capita growth rate. This one's our little r, and we're going to spend a lot more time working with little r. And so little r equals our birth rate minus our death rate. Notice though that we're doing this per capita now. Per capita birth rate and per capita death rate. Just meaning that how many deaths do you have per 100 people, for example? How many births do you have per 1,000 people? That's what it means to be per capita. We're going to take this formula, R equals B minus D, and we're going to put it into our population growth model, and then we're going to manipulate it quite a lot. All right, any questions about little r? And again, this is your long-term, your instantaneous, your long-term. And in this model, the exponential growth model, which is what we're about to work with, it's not going to change either. When we get to logistic growth model, it's going to change, but we're not there yet. Okay, we're still doing simples here. So now we've got these italicized D's. And I know they cause some confusion for people. We can't really do anything with these italicized D's. It just means an instantaneous change. To get a formula that we can actually do homework with, we're going to have to do some calculus to get rid of those. Don't worry, we're going to have a magical box where the formula will come in, the calculus will happen in the magical box, and we'll get a new formula coming out. Okay? So sometimes I'll get some questions about what should I put in as my D, and the answer is we're not working with those. Okay? That's an instantaneous thing that is there's another word besides symbol. But anyway, it's a symbol that we're not working with. All right, but we are working with those N's and T's in this formula. Okay, so this is an instantaneous change in population size divided by an instantaneous change in time. And basically it's just saying, how is the population changing over time? That's all it's really saying. Now our formulas will start with that for the most part, because that's what we're interested in. How is the population size changing over time? Okay. So like I said, we're going to work with two models. We're going to work with exponential growth and logistic growth, and then we're going to learn how to modify the logistic growth a little bit. Exponential growth is a lot easier to work with in terms of mathematics, because we're going to take the formulas for exponential growth and we're going to force them into a straight line, and that makes them fairly easy to work with. As opposed to the logistic growth models, it's a lot harder to take a curve like that and turn it into a straight line, so it's a little bit more complicated. So we're going to start with exponential growth this week. We won't hit logistic growth till next week. Exponential growth is characteristics of population living in an unlimited environment. So this is an ecology class. How likely does that seem? It is unlikely that they live in a truly unlimited environment. However, there are times in which animals will populate an area that seems unlimited. So for example, if you're the first of a group of organisms to colonize a new island, then essentially at that moment, your population size is small, you don't have any competition, resources are abundant, and we would expect that population to grow exponentially, right? They use this a lot in micro as well. So the petri dish represents an environment. It has limited resources because it's a petri dish. However, when you put the bacteria on there initially, there's no competition, there's lots of resources, and they grow exponentially, okay? And so when we talk about colonizing species, for example, when they colonize a new area, this is the type of growth you'd expect initially.
Could that be used to describe, like, I know there's still competition, but like invasive species that don't have any natural predators?
Initially, at least. At some point, they'll start to compete with each other, right? For resources, you get intra-specific competition, and that's going to complicate it.
Okay.
And we will eventually have models where we incorporate intra-specific competition, and models where we incorporate predator-prey interactions. We're not there yet, though. We're just trying to get this basics going. All right. Populations can overshoot their environment, so kind of set you up for that a little bit. And so if you had some micro, you graph it and it grows exponentially, but eventually it runs out of resources and it tanks. This is typically what happens. And wild populations, you see the same thing. They tend to overuse their resources until they overshoot, and then they tank. And so this is characteristic of populations introduced to new or unfilled environments, for the most part, as we've been discussing. Should have just got all the bullets up there at once. And I will say, I'm going to focus on exponential growth, and then later we're going to focus on logistic growth, and then we're going to take the logistic growth model and we're going to manipulate it to get other models. But as I've pointed out before, anytime you're working with a model, not a bottle, but a model, it's going to never be exactly like that in the environment, right? So we're going to take the exponential growth formula, we're going to turn it into a straight line, and the reality is a real life situation isn't ever going to be a straight line, right? However, keep in mind that what we're really doing is we're averaging across a lot of years to make a prediction. And so if we take a sample here, take a sample here, estimate into the future, we're extrapolating out our straight line, that gives us a point in the future that we think we're going to reach. Like we think that's what the population size is going to be. If we really got into these models a lot heavier, we would not only have that point in time and what we think the population size would be, we would have error on either side, right? Plus or minus this many organisms. And then you're getting into something that you can start to plan for, essentially. All right, so here's the exponential growth model. Here's its basic form. So if I ask you for a basic exponential growth model, this is what I'm looking for, nothing fancy. We are going to have some other graphs, so I need you to be able to tell them apart. This one is just the simplest population size and how it changes over time. So this is dn over dt, essentially, how the population size changes over time. Exponential growth is often called a J-shaped curve. It's kind of a lane J. And what you see is it's fairly flat at first. Why is it fairly flat at first? Because you don't have that many individuals in your population reproducing, right? There are limits, and we're going to put those limits into our logistic growth model later. But you're limited by gestation, for example. If you can have a baby every day, then your population will accelerate a lot faster. If you can't have a baby but every 3 or 4 years, then your population is going to accelerate a lot slower, essentially. If you're microbes and you're populating every few minutes, you can really do some super cool exponential growth quickly. Right? All right, so you start out slow because you don't have that many individuals, and then the growth accelerates, which is very characteristic of an exponential growth model. That's what gives us our J shape. This is your dn over dt, essentially, so your population size and how it's changing over time. However, it's very difficult to do mathematics on a curved line. And so we're going to need to change it. We need to change it into a straight line so that we can work on it. This is the basic. Anybody have questions on our basic graph? Just change your population size over time. So, the first thing we need to know is our exponential growth model assumes that the birth rate and the death rate are constant. The birth rate and the death rate are constant. Since our instantaneous per capita growth rate, or little r, equals your birth rate minus your death rate, that means that little r is also constant in this model. Okay. It's not clear on this slide, but we will have a slide that expresses that clearly. All right, since our birth rate and our death rate are constant, we can say that our change in population size over time equals the number of individuals we have times our birth rate minus the number of individuals we have times our death rate. So why are we taking our population size times our birth rate and our population size times our death rate? Because that actually gives you how many births you have over time and how many deaths you have over time, right? It's usually like, I don't know, 10 births per 100 individuals or something like that, right? And so if you have 5,000 individuals, you need to turn that into the actual number of individuals being added. Okay, it's going to depend on your population size. So I don't remember what the birth rate, we looked it up in here one day, didn't we? The birth rate in the U.S. But whatever the birth rate is in the U.S., you know, you want to take that, multiply it times the U.S. population, and that tells you how many people we're actually adding to the population over time.
I don't think we looked at the birth rate exactly. I think we looked at the census.
We looked at the census, but it had the birth rate, the death rate, the immigration rate, and the immigration rate.
Okay.
I remember we did it because y'all were asking me something, I think, about immigration or something. So I pulled it up. Yeah. But it had all of that. It's had number of births per minute, I think. It had number of deaths per minute, and then immigrants per minute, something like that. All right, anyway. So now, in the middle here, we can use algebra. Luckily for y'all, you don't have to do it. I have it already done for you on the slide. We're going to factor this out. First thing we're going to do, we haven't even done that yet. All we're doing right now is we're taking this out. And so we're just factored out the n to equal times our birth rate times our death rate. N times our birth rate minus our death rate. And then we've said, well, B minus D equals R. And so we put R in. That's all we've done so far. All right. This is the formula for exponential growth right here. dn over dt over Rn. This is the one you need to know. Okay. As we go forward, and specifically as we go forward into logistic growth and beyond, what I'm going to be asking you to do is identify different parts of the formula. For now, all that means is what is little r, what is n, right? That's all we've done so far. But in the future, we're going to add to this formula, and I'm going to ask you something on the, well, we might do a little bit on this first exam, on the October 30th exam. So circle the part of the equation that represents exponential growth. That's a pretty common question I ask. Circle the part of the equation that represents exponential growth. You would circle this, right? No matter what else we've added or multiplied or whatever, this is the part that represents exponential growth. And it's going to stay with us as we move into these other models. So it's really important that you know that formula. Okay. This formula, by the way, if all we do is we add a 0 to it, it becomes a formula for a straight line. So if I add 0 to that formula, have I changed it in any way? No. All we did was make it have more things in there, but plus 0 isn't going to change what's happening with the formula. All it does is make it clearer that it is a straight line formula. So like I said, we'll review that. So in the middle of this slide, you have your standard formula for a straight line, which is y, just referring to your y-axis, equals mx plus b. X is your x-axis. M is the slope of the line. And b is where your line crosses the y-axis also known as the y-intercept. So where it intercepts or crosses over the y-axis. All right, and so what I've done at the bottom is I've gone ahead to show you what belongs, what represents each one of these in our formula. And so our y-axis is going to be dn over dt, or an instantaneous change in the population size over an instantaneous change in time. It's a mouthful. I'll be glad when we calculate them out, which we're about to do. So that's going to be our y-axis. So I'm going to cheat and go forward just for a second. See, our y-axis. Our x-axis is going to be the population size. So we go forward, here it is, our population size. Our y-intercept, in this case, that's where b is in the formula. That's where our 0 is. So we added that. And so this is a homemade line. So I'm not quite perfect, but it should be intercepting right at 0. That's our y-intercept, is at 0. And then finally, m, you compare it up there, is r. So the slope of the line is r. Okay? The slope of the line is r. So this basically just has the same thing as the bottom. I don't know why I bounce back and forth. It's at the top of this slide too. Probably because it's Monday. Okay? Now, that's a formula we can now work with. So hopefully, even if it's been a while since you've worked with a formula for a straight line, hopefully a few things are kind of fluttering up to the surface, like rise over run. Remember that? And so if you have rise over run, then you can figure out what the slope of the line is, which means if we have a population, we have the population size at 2 instants in time, we form our line. If we can get the rise over run, we can calculate its growth rate, which is where we're headed, essentially. Okay? Any questions so far? Okay. So at the top here, we have our exponential growth formula again. We'll say it a lot. dn over dt equals rn. dn over dt equals rn. Now what we can do is solve for little r, so we can figure out what our growth rate is. And so to do that, what you would do is you would divide both sides by n. But notice I flipped it over on you, so we have r equals dn over n dt. So all that happened between the first formula and the second formula to get our little r is we divided both sides by n. I also have a reminder on this slide, which is always good at this point, that sometimes I'll ask you some general questions, and so if if r is positive, that means that the growth rate is positive and it's growing. If r is negative, then the population is decreasing. And if r is 0, then neither is it increasing nor decreasing. It's stable. For the most part, I think pretty much always, when we're working with our exponential growth models, they're going to be positive. As we move over into a logistic growth models, it'll become more complicated. All right, this next slide is going to tell us what happens to r over time in this model. This is a boring graph. It should be the easiest graph, because we already know that one of the assumptions of the exponential growth model is that r doesn't change over time, right? That's what we're assuming. The birth rate doesn't change, the death rate doesn't change, therefore the growth rate doesn't change. It's constant no matter what period of time we're looking at. All right, and so on the next slide, we just have dn over n dt, which I have the reminder at the top. That just means r, whatever r is. And if we look to see what happens to r as the population size increases, it stays the same forever and ever 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 in the model. We know in reality that's not going to happen, but in the model, that's what the model is doing. R is the same no matter what the population size is. It's always going to be the same in this model. Okay, any questions about this one? And so what we're going to do next Monday, woo! Mind-blowing Formula Mondays. That's why we're going to take a break and do polygyny and stuff. What we're going to do is we're going to say, all right, here's what R did in the exponential growth model. Now what does it do in the logistic growth model? So we'll compare this graph to a logistic growth graph, essentially, and see what happens to R. And then it becomes more exciting. Woohoo! In other words, it's not a straight line. Okay. But that was the point of looking at it right now. R is the same forever and ever, as is the assumption of the exponential growth model. We're getting there. We're almost ready to actually do some math. All right. So, like I said earlier, those little italicized D's in our formula, we can't really do anything with them. All right. And so what we need to do is we need to use some calculus to get those instantaneous change variables out of our formula. And so that first bullet there is our magical calculus box. And if we put our exponential growth formula through our magical calculus box, it spits out the formula underneath that bullet. So the NT equals NOERT, also known as the no-work formula. All right, be careful as you're writing it down. And so it's N with a subscript of T. I think that one's pretty obvious. N with a subscript of 0, which means we're going to always start with our initial population size. So N at time 0, that's what that 0 is, N at time 0. E is the inverse of the natural log, which is why we're going to use our calculators for like a minute today. R is our growth rate, and T is our time. When you're working with this formula, whatever time you have right here should match that time right there. These two numbers should be the same. Right? If you're calculating the population size at 8 years, and then this T up here is also 8 years. Okay? All right, before we go any further, let's get your calculator out. Everybody have one? Okay. Across the top line, you have an on button if you ever need it. If you ever open it and it's not automatically on, you can hit that. That's in the top right corner. And then right beside the on button, you see LN. That's their natural log. And then right above the LN in orange writing, you see e to the x. Okay? And then on the top left corner, you see a blank button. And above the blank button in orange, it says shift. And so that shift lets you do the things that are in orange, essentially. All right, but let's play with it for a minute so that we try to understand what it means to be an inverse of the natural log. And so I'm going to put in the number 8. And then I'm going to go up and I'm just going to hit the natural log button. So I'm just hitting LN. And I got 2.079441542. Everybody can do that? I don't think we've done anything too hard yet. All right, now hit the shift button. And then hit the natural log button again. It's magic. Wow, it's an inverse of the natural log. It just turned it back into what it was before. All right, that's all it's doing, okay? And that's how you use that part of the calculator. We can do another one. Ooh, let's do 3. Got 1.09861228.9. And then I'm going to hit shift, get the e to the x, and oh, it's 3 again. Okay. Anybody get stuck on that? You're like, if this stays like this, we're okay, right? All right, let's work our first formula. First problem here. Okay. These are going to be word problems. And so what you need to do is you need to read the problem and kind of write down information that it's giving you. As you're doing this, make sure before you do any math that you read the entire problem. And I say that for lots of reasons, but also because a lot of times if the unit is not years, it'll say the unit at the end of the problem. Okay? And so there's one in your homework, I think, that says 4 weeks for now, and then it says to use days. So 4 weeks from now would be 4 times 7 or 28 days, right? So it can be a little tricky. So make sure you read the whole problem and you know what you're working with. All right. And so we have a population of 100 gray squirrels. That's going to be our population size at time 0. Switch from wood. That's way off. Let's see. So our N0 is 100. It has a rate of increase of 0.01. So this is, you're going to find, is your easier problem. This is the problem you want because it gives you R. You don't have to find it. How large will the population be in 8 years? And so our time is 8 years. What are we actually trying to solve for?
The population size.
We're trying to find N8, right? That's what we're trying to solve for. What's the population size 8 years from now? Okay. Noticed that I have that part on here. I don't know when I typed it in. I had shoulder surgery one year. That's probably when I typed it in. So we're solving for N8. We're going to use this formula. And so it's going to become N8 equals 100. E is the inverse of the natural log, so it stays put. R is 0.01. And T is 8. So it becomes this. Okay. To do this formula, what you want to do is start with the exponent of this. It's not exponent. Is it exponent? Whatever. You want to start with this part. So you want to take 0.01 times 8, and I got 0.08. Is that what everybody got? All right. And then what you want to do is, because we're taking the inverse of the natural log, is hit Shift and then hit the LNEX button. And I got 1.083287068. By the way, we'll round to 2 decimal places on all this stuff. And then I'm going to multiply that times 100. And so what's our answer to our question?
New population at 8 years is 108
Good.
individuals.
Should I put 108.33? No. The 2 decimal places will be for everything except when you're actually estimating whole animals, right? And so correct. So we have 108 squirrels 8 years from now. If we start out with 100, we have a growth rate of 0.01. 8 years from now, we would have 108 squirrels.
Do we always round it down?
I tend to round normally, I guess, 0.5 up, below 0.5 down. But that's not something that I couldn't catch. As long as you're like 108 to 109, I'll be like, oh, okay, I got it. But later on when you're doing your homework, where we have a population size in the future, there's one that's like ends up being like, I don't remember, it's 12 million or 12 billion. It's a huge. And if you round differently, because the numbers are so big, you'll be off by several million, right? So it's kind of weird. Yeah. Which I can usually figure out, but I'm less grumpy if we all round the same way so that we're in the ballpark. All right. Now, this is our working formula. NT equals NOERT, a no-work formula. However, I am going to ask you all to work with it in 2 different forms. Okay? Everybody just loves it. I'm just kidding. Everybody hates it. But I am going to ask you to do it. It's important. And so we can take this formula and we can actually modify it into the straight line formula again. And it has some practical uses, which is why we're going to do it. All right. And so the first thing we need to do is get rid of the inverse of the natural log here. And so to do that, you take the natural log of both sides. This is something we need to know anyway. It's really easy. And so right here, when you take the natural log of the inverse of the natural log, whatever you have right here comes down. It just cancels each other out, and those numbers just come down. Okay? We don't have to do anything fancy. Don't have to poke anything into the calculator. When you take the natural log of this, it just becomes the exponents up there. Okay? But we have to take the natural log of everything, and so we end up with this formula right here. So this is the other working formula we're going to use. And we're going to see that on the next slide. Alright, and so again, what we've really done is we've taken that formula and we've turned it into the formula for a straight line. So that Ln, the natural log of n, that becomes our y-axis. Time becomes our x-axis. The slope of the line is still r, just like it was before. But now we actually are going to have a y-intercept. It's going to be the natural log of n sub 0. Alright? Which means that we can make this graph. And so if we wanted to make this graph for this data right here, what we would do is we would have years along our x-axis, and we'd start with 0, 1, 2, 3, 4, 5, 6, going out to 8. And then we would have to take the natural log of n sub 0, which was n sub 0 was 100, which comes out to 4.6. So I need to make my scale, and wherever 4.6 is, that's the natural log of n sub 0. And then we've already done that problem. It ended up being 108. And so at 8 years, the natural log of 108, whatever that was, that would be our second point. We connect them, and the slope of that line would have been our 0.01, essentially. Did y'all follow that, more or less? All right, looks like we got a new problem on the next slide. Okay. And so we have a population of 100 gray squirrels. So we can write down our n sub 0 is 100. 10 years later, you resample the population and it has grown to 118 squirrels. And so our time period that elapsed was 10 years. Should be better here. Keep up with your units. 10 years. I lost one. There it is. There we go. 10 years. And our population size at year 10 was 118. And in this case, we want to solve for R. What is the instantaneous per capita growth rate? Okay. And so now we can just poke things into our formula. And so n sub 0 is 100. That's also our intercept. So the natural log of 100 is right there. We know at 10 years, the population size is 118. So n sub 10 is right here. So natural log of 118. We don't know R. That's the only thing we don't know in this formula. But we do know T, and T is 10. All right. So what should we do first? Looks like I didn't do that in your homework. Okay, homework. I'll do it over here. On the slides, I didn't do it. All right. So natural log 118. Okay, so I'm just going to put 118 first. I got 4.77. Alright, I'm going to do 100, which I think we just did, didn't we? 4.61. Is everybody okay? Alright, so now what do I need to do? I'm going to subtract 4.61 from both sides. That's going to cancel each other out. That's going to not be a very big number. I got 0.16. And then what do I do? Divide both sides by 10. Uh, 0.02. is my little r. Not so bad, we did that in like 1 minute. I know that because I checked to see how much time we had left. So we did that in exactly 1 minute. Any questions on how to do any of that? We'll get lots of practice on Wednesday. Okay, so what's the benefit of this problem, or this equation? Is that we can graph raw data over time, we can fit a line to that, and we can figure out the slope of the line based on this model to get the R. Okay, we don't always have that information. That other formula is good. The no-work formula is good if you have 2 points in time. This one is able to accommodate lots of points in time, which is more realistic and going to give you a better model, essentially. Does that make sense? That's what that's trying to tell you. And so the original model, you only have 2 points in time is all it'll accommodate. This model, you can do a scatter plot, fit a straight line, and go from there. So it's a lot more practical in reality. And that's why you have to use both. Okay. So generally what we'll do on the homework is I'll have you do both the no-work formula and this one, and we'll practice that on Wednesday. On the exam, especially the first one, I'm usually specific, use both. And then on the final, a lot of times because we're trying to be faster on the final, I've got new stuff on there, I'll say use whichever formula you want. Right? But for now, everything will probably be both formulas, will likely be both formulas. What I found last year was some people actually ended up preferring this one. In some ways it is a little bit easier to use. So here's our practice problem. And there's our second practice problem, but we'll do those on Wednesday together, and then you'll have your next homework assignment. Okay, we made it.